Welcome back to HEC Physics. This is a follow-up video on DC circuits. In my previous video, I have explained the key concepts of DC circuits. And in this video, I'm going to show you an example of how to do the analysis of such a circuit. So this video is focused on looking at an example of a circuit and then how do we calculate different quantities of that circuit or how to do analysis of the circuit. So the example I'm going to consider is where I have a resistor and it's 10 ohms, which is connected to another resistor. This one is 20 ohms. And then there's a bulb connected to this 20 ohm resistor. And as you can see, it's on a different branch. So this part over here, the bulb is connected to the 20 ohm resistance in parallel. So the first thing we are going to look at is how to calculate the total resistance of this circuit configuration. So we have one 10 ohm resistance and then we have two separate resistances, 20 ohms and 30 ohms. So we have to start with this part of the circuit here. So this is a combination circuit. You have both series and parallel connections. So we'll start with this part over here. And then we are going to find out what is the total resistance of this 20 and 30 ohm resistor. So we'll start with that. Okay. And as you can see, these two resistors, because they're connected in parallel, so we'll have to use the formula for parallel circuit. And we know that for parallel connection, this is the relationship between the total resistance and the individual resistors. So we'll use that formula and then we can work out what is the total resistance. And by the way, sometimes this total resistance is referred to as effective resistance as well. But what it means is what is the combined resistance of that part of the circuit. So the first one I have is 20 ohms. The second resistor we have is 30 ohms. And remember how we have to take the inverse to get the total resistance. So this you can just simply plug it into your calculator and get the value. Or you can use the fraction method. And over here, if you use the fraction method, you will get 5 over 60. And then you have to inverse it. So if you take the inverse of it, it will be 60 over 5. And that gives us a value of 12 ohms. So this part over here, the total resistance of this part is simply 12 ohms. Okay. So now what we need to do is we basically can redraw this circuit configuration. We still have the 10 ohm resistor over here, but then we can replace the second part of this circuit with a single 12 ohm resistor. So you can imagine as if we have these two resistors now in the circuit. So this is this part over here. So now as you can see, the 10 ohm and the 12 ohm resistors are connected in series. They're on the same branch. So then we can work out the total resistance of these two using the series formula. So the total resistance of this 10 ohm and the 12 ohm resistor, we simply have to use the series connection formula, which is R total is equals to R1 plus R2. And then if I put the values in, 10 plus 12, I get a total resistance of 22 ohms. So that's the total or effective resistance of this entire circuit configuration. For the next part of the analysis, we are going to connect this circuit configuration over here to a power supply like this. And let's say we have connected it to 12 volts. And then now we have a closed path for the current to flow. So current will flow from the positive terminal of the battery, that's the direction of conventional current, through these components over here. It will come to this junction, split up into two parts, go through these two branches, and then come back like this. So that's our current I. And let's say we have to calculate, so number 2, we want to calculate this total current I. What's the total I in the circuit? To do that, we will use Ohm's law, V equals to IR. And because we want to solve for current, so we'll rearrange this equation. I is equals to V over R. Move this R to the other side of the equation. And when you're solving for total current, then we will have to use the total voltage of the entire circuit, which is 12 volts over here, and then divided by the total resistance of the circuit. And we have previously calculated the total resistance of the circuit is 22 ohms. So let's use that, 22. So then if you use your calculator and then do 12 over 22, let me do that quickly, 12 divided by 22. So we get 0.5454 recurring, and I will round it to 0.55 amps. So that's the total current in the circuit. Next, I will show you how to calculate another quantity, which is, let's say we want to find out the voltage across the 20 ohm resistor. So I want to find out how much is the voltage across 20 ohm resistor. Okay. So to answer this question, what we need to understand is the current that we have calculated previously, 0.55 amps. That current goes through the 10 ohm resistor first, and then it comes to this junction, and then it splits up into two branches. So some of it goes through the 20 ohm resistor, and some of it goes through the 30 ohm resistor. So if you want to find out the voltage across the 20 ohm resistor using Ohm's law, V equals to IR, then I know R, but I also need to know I, how much is the current through the 20 ohm resistor, to use Ohm's law to figure out this voltage. Right now, I don't know how much of this 0.55 amps current is going through the 20 ohm resistor. So what I'm going to do alternatively is I'm going to first use the fact that all of this 0.55 amps current is going through this 10 ohm resistor. So I can easily work out what is the voltage across this 10 ohm resistor, because I know the current through that 10 ohm resistor is all of that 0.55 amps, because there's no branching out, no splitting of the current before that. And we also know R for that resistor is 10 ohms. So we can use Ohm's law, V equals to IR, to work out the voltage across the 10 ohm resistor will be simply I times R, and that is 5.5 amps. 5.5 volts. Okay, so once I have worked that out, then I can look at the circuit and understand that if this part of the circuit is using 5.5 volts and the total voltage across the entire circuit is 12 volts, then the remaining voltage is going to this other part of the circuit. So that means this part of the circuit over here is getting the remaining voltage. So I can work out the remaining voltage is 12 minus 5.5, that is 6.5 volts, and the voltage across these 2 points here is this remaining voltage 6.5. So either branch over here, so both branches over here will get that exact 6.5 volts, because we know the voltage across each branch in a parallel connection is the same. So that's how I can figure out that the voltage across the 20 ohm resistor will also be 6.5 volts. Okay, so sometimes this is the strategy you will have to use. If you can't work out the voltage straight away using the current and the resistance, then you have to check, is there any way I can work out the voltage using other methods? And that's what we have done here. Okay, so next let me show you an explaining question where you have to explain how the brightness of the light bulb in this circuit configuration over here will change when this 20 ohm resistor here is replaced by a 30 ohm resistor. So if I change this 20 ohm to 30 ohm, we have to explain how the brightness of the light bulb will change. So we'll start with thinking about what is the brightness of the light bulb determined by. So what does the brightness of the light bulb depend on? And if you remember brightness, we have to remember that brightness is associated, is dependent on, or brightness, sorry, I'll just write like this. Brightness depends on power, and power depends on current and voltage. So we have to check what will happen to the current that is going through the light bulb and what will happen to the voltage across the light bulb in order to explain what will happen to the power. Now this current and voltage, because we are specifically talking about the brightness of the light bulb, we have to check what will happen to this current over here and what will happen to the voltage across the light bulb as we make these changes, or this change over here, replacing the 20 ohm resistor by a 30 ohm resistor. So you need to remember that if you increase any of the existing resistances in the circuit, then that increases the overall resistance. So when the 20 ohm resistor is replaced by a 30 ohm resistor, the total resistance of this entire circuit increases. Okay, so that's the key. And if that increases, then we know that I total, the total current in the circuit, which depends on V total, the total voltage across the entire circuit, divided by R total. If R total increases and V total stays the same, you have to mention that V total is staying the same, then I total will decrease because you are increasing the denominator over here. So the total current in the circuit, so I total, decreases. And if that happens, because the total current, this I over here, now it's less, so that means the current going through the 30 ohm resistor will also decrease. 30 ohm light bulb will also decrease. So that means the I through the current through the light bulb decreases. Okay, so we have explained what happens to this I over here. We have mentioned that I decreases. Now, what will happen to V, the voltage across the light bulb? The voltage across the light bulb here, V, depends on the current and it depends on the resistance of the light bulb. Now, because current is decreasing, resistance is staying the same. So we'll say the voltage V across, or V of the bulb, V of the bulb is I of the bulb times R of the bulb. Now over here, I is decreasing, so I decreases, R stays the same. So then what will happen is V decreases as well. Please do mention both quantities. What happens to both quantities? Over here, because the voltage depends on both current and resistance, we have to say that I is decreasing, but R is staying the same. So the combined effect of these two is that the V of the light bulb decreases. So both I and V decreases through the light bulb, and therefore power of the bulb, I'm always writing it like this. Power of the light bulb, which is equals to the current and the voltage. So I has decreased, V has decreased, so therefore P will decrease as well. So this shows us that the power of the bulb decreases because both I and V of the bulb decreases. Therefore, final conclusion, linking it back to the question, the brightness of the bulb will decrease. Okay, so that's how we answer questions like this. I hope that's clear. Of course, there are many more changes that you can make to the circuit. You can add another resistor. Depending on how you add another resistor, whether you add it in series or whether you add it in parallel, things will change differently, and you have to carefully analyze what is happening to the current, what is happening to the total resistance, and then justify your answer. Always look at the formula, and then based on the formula, check which quantity will change when I make these changes to the circuit, and then answer your question accordingly. So this is where I'm going to finish today. If there are any specific question that you want me to answer, if there's any past exam question that you want me to go over, please let me know by commenting below, and then I will make a video on that. So see you next time.